Hello. Hello. Yeah, so Barista might be pushing it a little bit far, but my domain name is coffeecode.net, and I do roast my own coffee, so that's worth something, I think. So I'll admit, by day, most of what I'm doing is Perl with the Evergreen open source library system. It's been around since about 2006, so it's got legacy roots, and we keep on rolling with the legacy code. But when I get the chance, I like to program in Python. So at night, or for greenfield projects that I get to work with at the university, my go-to choice is Python. So I want to point, if you want to, you can go and grab this from Gitorious DBS or at github.com/dbs. There's a Postgres full-text search engine application. I promised in the description full-text search engine in 200 lines of code with PostgreSQL. I think I achieved that with a little bit of fun along the way. It's simple, so don't expect to go too deep, but that's what I'll be talking about for the most part. It's based on a real project that I've been working on as well, though. So that project was, last summer we got grant funding at the library at Laurentian University to digitize 50 years of our student newspapers, which is over 1,000 issues, including all the full text, all the images. Which is a great sort of retrospective on student perspectives on events that may have happened at around Sudbury or in Ontario over the last 50 years, the entire history of Laurentian University, basically. So we got those all scanned, student power to the max, posted them all to the Internet Archive. So archive.org is an awesome project. They handle all the bandwidth. It's freely distributed. Everybody can find them and grab them. And they OCR the text as well, so they do optical character recognition. We can get the text back. The one major problem that we had was that Internet Archive does not at this point offer a great way of doing full text search within a particular collection that's been uploaded. So as a result, we needed to provide a local solution, which means that I got to build something from scratch, which means that I got to play with Python, which makes me happy. Now, we were already using PostgreSQL to do sort of a basic quality assurance app. We wanted to make sure that the students that were working on the project were providing the metadata that we needed for each issue on an issue-by-issue basis. 1,000 issues is a fair amount. And once the grant funding goes away, then you don't get magical students to come back for free. So we already had a whole lot of metadata, things like the name of the newspaper that was in play, because we had about 3 major different newspapers over that period of time. The volume, the edition, the publication date. And so that gave us the ability to do a simple application that would say, well, we're interested, maybe Alumni Affairs was interested in putting together a collection around a particular year because they've got a reunion coming up. So we could give them a year basis. But we also wanted to be able to search for interesting strings in the full text for useful information for outreach, possibly to find embarrassing stories about people who are now public officials, those sorts of things. So a common approach for a project like this is to take the full text and make sure it all goes into a dedicated search engine like Solr or Sphinx. Many of you have probably used those before. And then build a search interface on top of that. The reason I wasn't a fan of that approach was I don't have a whole lot of resources, staff resources, so DevOps is sort of what we live with at library, so keeping things as small and simple as possible is a real bonus, and the amount of traffic that we're looking at is probably not going to be, scaling out to startup levels, right? So PostgreSQL actually has featured full-text search support in its base set of features since 2008, when 8.3 was released. And I've been using Evergreen since 2006, and it relies on full-text support. We have about 3 million items that we're tracking in our instance of Evergreen on a single database, which explodes out to about 50 million rows or more of full-text search that's going on. So it's pretty sure it could handle the 1,000 issues, albeit with much larger documents. So I decided to keep on using PostgreSQL and see how far we could go. So the core of this talk is to focus on the PostgreSQL side of things, because PostgreSQL, as many people don't recognize the functionality that's in PostgreSQL, or it's a little bit foreign to them. So this is an example of the 4 sort of basic statements that are in the demo application for creating a full-text search schema. It's a table that's enabled for full-text search. The first one is a table that includes a TS vector column alongside a text column, right? The TS vector column, we don't have to worry about too much in terms of actually populating it ourselves because we can take advantage of PostgreSQL's feature of triggers so that on every insert or update to a particular row in the table, a trigger can be called, which automatically maintains or changes the state of data within the same row. It can actually have effects outside of the rows as well, but for our purposes, we're interested in this. And in that case, it's calling the TS vector update trigger. That's a built-in option within PostgreSQL. You can write your own triggers to do this. But the TS vector update trigger just takes an incoming doc column and updates the TSV or TS vector column accordingly to create a text search vector. Sorry, I should have said TS vector stands for text search vector. All throughout PostgreSQL, there are TS functions and TS types. All of these are text search types. It took me a surprisingly long period of time to recognize that connection. So to provide good performance for the application, even though we're looking at 1,000 rows, table scans take no time. You could keep it all in memory. Still good practice to define good indexes for your relational database. So we create an index on it using the gin type of index. Gin is oh great, I don't really want to connect right now, thanks. Gin is a generalized inverted index. There are two basic types of index used for full text search in PostgreSQL, gin and gist. Gin takes a little bit longer. There's a little bit more overhead to build the index in the first place, but the performance on queries is better. So in general, unless you've got a really good use case or reason why you want to lower your overhead on building the index, gin is the way to go. So then at the bottom, the example is just inserting a couple of rows. All that we're inserting are just the text documents, and the TS vectors are being generated for us automatically by the trigger. So that's really it for a basic out-of-the-box sort of full-text search engine on the database side of things. So to go a little bit deeper to find out what PostgreSQL is doing for us, because magic is great, but sometimes it's better to understand what's going on underneath, you'll see that every text document gets parsed into tokens. So I was just sitting in on the C Python talk that Brett Cannon was giving about parsing in tokens. Similar thing is going on here. So the full text search support recognizes things like words or white space or numbers or URIs. And then you can configure PostgreSQL, but it comes out of the box with a number of reasonable defaults. Different sorts of normalizations to occur to each one of those types of tokens. So words, for example, will get folded to lowercase. They'll be stemmed if you're using a language that there's a stemming algorithm for it. Stop words may be removed. Those sorts of normalizations will occur because you want your incoming queries to match the words that you have in the database. URIs might have www stripped because who uses www anymore? You want them all to be the same, whatever. And then finally, the text search vector for the text document has been created. So that text search vector, scrolling off the bottom of the screen, sorry about that, but you can see the incoming document said sketching the trees, and our vector is a vector data type. As you can imagine, we have sketch and tree. They're all lowercase. They've had their suffixes stripped off, and you see the positions appearing after them. So 1 and 3 are the positions that they occurred in the string. The stop word the has been stripped out. If there are multiple instances of tree, then you'd see multiple numbers indicating their position within the document. The reason those positions are important is because it affects the relevancy ranking. So PostgreSQL comes with relevancy ranking algorithms out of the box, and it makes sense for, say, the cover density algorithm to have two terms that are closer together, representing a higher relevancy of document when you do the search. So that's what's going on underneath the covers. So really, it's just to take advantage of this support. Once you've got your schema created and you've populated the table, all you need to do is just issue a straightforward SQL query. Well, it's a bit of a doozy of a query for some of the basic ones. There's a lot going on here, and you can write this different ways. Everybody has a different approach, but I like to use the with clause. It's a common table expression. Essentially what that's doing is it's defining subqueries, what you might use as subselects within the major select statement at the bottom. It's defining them up front, so I can reuse them with a simple alias after the fact. So at the top, we're defining the query using the toTsQuery function. The toTsQuery function says, okay, give me a hunk of text. I'm going to parse that. And you can pass in things like Boolean operators. So in this case, it's got an and, saying it's got to be, these two terms both have to appear. But you can also use wildcards. You can use negation operators. There's a few different types of operators that you can pass into a toTsQuery. I believe in the demo application, I cheat a little bit because I didn't define my own parser to handle all those. And I use the plain toTsQuery function. And that just says, okay, I'm just going to and everything, whatever you give me. But that also avoids a whole lot of failure cases, and it matches most of what our alumni affairs type people would be doing. The second query that the second subquery that we're defining, the ranked query, we're actually doing the ranking of the documents. So one common mistake that people make when they're using PostgreSQL to do full text search and they're doing ranking is they'll call the tsRankCD function and they'll end up doing a table scan because they haven't limited the tsRankCD query to running across just those documents that actually match the search query to begin with. So we're doing that by using the @@ operator. The @@ operator, one of the fun things with PostgreSQL is that different data types can have different operators defined for them. @@ is the text search match operator in this case. You'll find many other ones if you've used PostgreSQL before and use different data types. So finally, now that we've defined those two subqueries, our actual search query becomes even simpler. So we just say, select the ID and the TS headline. The headline is going to be when you do a search and you get snippets showing the context of your search terms within the document that you had searched against and it found hits. This is what the TS headline function is doing. It's just returning snippets to us. And it's configurable, it's all totally configurable in terms of how many matches you might have per document, what type of markup you want for the matching terms. But by default, it gives you bolded terms in HTML B tag. So we call the TS headline function, and we're using the subqueries that we defined before, and we're going to order it by the ranked order descending. I've hard-coded all the values like the limit of 10, and I haven't put any offset, and we've got toTsQuery with a hard-coded query, but in the demo application, we actually have variables defined for that, so you can actually have paging through the results. So really, it's just 3 lines. Just ignore all the common table expression up above that. So to talk a little bit about the design of the application, because this is also talking about Flask, a tiny bit about Flask, mostly about PostgreSQL. I decided to define a kind of a 2-tier architecture. There's a harvester down at the bottom. All that does is it goes out to the Internet Archive for a defined collection, grabs all the metadata, and gives us some of the images. So we've got those locally so that we can use those in our application, serve them up. It stuffs the metadata into PostgreSQL and stuffs some of the collateral onto the file system. That's a Python 3 application, because hey, Python 3's out, thought I'd use it. The REST application sits and talks directly to the PostgreSQL database. It's using PyPostgreSQL to talk to it. In the demo application, it's a Python 3 application, and it's using Flask. And what it does is it accepts the incoming queries just as a RESTful, a very basic RESTful interface, and it returns JSON as the results. And there's another Flask application that we have sitting on top that provides the human interface, the UI for that. And that's also running Python 3 that serves up a simple form using Jinja 2 templates from Flask mapped to the search URL, looks at a couple of the query parameters and adjusts things accordingly. And it queries the REST Flask application, takes the JSON results and renders them for the humans to look at. The reason that I separated things out like this is because it gives me the ability to say if I don't like the REST application at the bottom, I can swap that out. I can swap out the PostgreSQL part with Solr, say, if we did, for some reason, blow up and every university wanted to use our application. I can do things with caching at either one of the tiers. I can separate it at the top And someone else could actually write queries. If they were a Rails programmer or a Java programmer or a Perl programmer, they could write their own front ends, and just we can use the JSON as sort of the coupling layer for things. So nice and loosely coupled. So one of the things that I decided to use Flask for this time, I've used Django in the past, I used web.py in the past. Admittedly, the routes as decorators just grabbed me right off the start as one of the most powerful and easy to use features within Flask. So as you can see, I'm just using the decorator to define multiple possible routes that are just going to the same function within my application. So we've got some optional parameters that are coming in of type int. So we saw in the pyramid application or pyramid presentation a little bit earlier in this room, same sort of thing, using regular expressions to validate. In this case, it's using actual types to validate. It has great documentation, and I think the world owes a lot to Django for how good the documentation was when Django came out. That a lot of other applications and frameworks have upped their game. Flask has great documentation. And it's got Unicode support throughout, which is important to Laurentian University because we're a bilingual university. So it's really important to get accents correct and not mangle things or break if people type in Montréal. So you can see the requests are happy to accept Unicode as well. So just a little bit on the novice side. Sorry if you're intermediate or advanced, but on the novice side, the JSON library is awesome for just taking a dict and serializing it in JSON format and passing it out in the wire. The Flask portion of this is just saying, okay, send a response back with a MIME type of application JSON. It's a serialized JSON that we're going to return back to the caller, which is so simple and delightful. And then up on the web application side, we have the same sort of search route for the separate web application. In this case, we're using the Flask arguments to request arguments to check to see if there's a query string and a page, because it's a simple get form that we've got defined in the templates. And then we do our usual quoting and encoding for Unicode purposes, and we then can mangle that JSON URL a little bit further. JSON U is standing for JSON URL, and we load the string. So JSON has the load_s function, which loads the serialization and creates a Python object on the side that on our side. So we can then pass that on to the template to render. So Flask uses Jinja 2 templates by default. You can swap that out with whatever you want, but those worked for me. So this is the same function continuing on. We're just calling the template environment. In this case, saying we want the results.html template, and we're passing in the couple of variables that can then be rendered on the human side. So this is what we have in production at this point, production-ish. It's kind of beta for our users internally. It's a very simple design. It's because I'm a very simple designer, and I do have a student, Emily Bamsey, who's working on this, so hopefully she's working on it. Well, not right now, it's the weekend, but hopefully she's working on it while I was on the bus on the way down here to add in some of the facet support that we have in the back end to render it a little bit cleaner. But if there are multiple snippets, then you have a plus sign that you can click to display all the snippets in place. And you can see search for Jean Chrétien provides a mix of student news as you would anticipate coming from student newspapers. So this application is available if you want to look at it. It's the second link here, gitorius.org/iaharvester. The demo application, as I said, is available online. We have great documentation from PostgreSQL and the full text search, although it's, I would say, in some ways, maybe a little bit too technical, hits you over the head very quickly. If I am allowed to say this, I'd suggest you take a look at my presentation from Postgres Open in 2012, which is a kinder and gentler 1-hour introduction into using it, and goes into a lot more depth than a lot of the options that you have with PostgreSQL. And the Flask and Jinja 2 official docs are great, as I said before. So with that, I'm right at 5:20, but I think We've got a few minutes before the keynote begins. If I could take a question or two, if anybody has any questions. Otherwise, I'm happy to talk with anybody throughout the rest of the conference. So there's a question over there.
Hello. Hi. So you mentioned your talk that in the libraries the traffic might not be the same growth as a startup. So just get me thinking that how often is you getting new documents to generate search index with? Is it like often, or is it like once a month or so? So if that's the case, have you considered like caching search results, storing your search, so you don't have to going to scan the search indexes every time?
Sure. So in this particular project, because it's student newspapers, we're looking at one issue per week, perhaps. So yeah, caching would be an option, but at this point, we don't really have enough load to justify adding it there. In the Evergreen project, we make use of memcache to cache searches, and so we're definitely familiar with that. But that's one of the reasons why the architecture is set up as it is, so that if we do find a choke point, we can try and address that. Number of different ways of doing that. Good question.
One other quick question. Last one.
Does the PostgreSQL text search do fuzzy matching, like for alternate spellings of words, or things like Montreal having the accent or not having the accent? Right.
So you have a couple of options there. By default, I believe you would need to add the unaccent contrib module and use the unaccent normalizer and add that. And that's reasonably robust. The other option in terms of in terms of fuzzy matching, you would want to use the trigram module, which is a slightly different approach than using full text search support. So that the trigram module can be used to generate search suggestions, for example, or adding that sort of support. I actually talk about that a little bit in the Postgres Open talk from last September. So, great question.